Hi there, my name is Tessa and I'm a tutor with Prep Expert. In May, I graduated with my Bachelor's of Science in Biochemistry and Molecular Biology and my Bachelor's of Art in Political Science. And next up for me is I'm going to be getting my PhD in Biology at the University of North Carolina in Charlotte. So you can imagine that I have a wide variety of interests, but my favorite subjects to study and tutor are AP Chemistry, AP Biology, and AP Government. But today we're going to be looking at an FRQ from the 2021 AP Chemistry exam. And so I like to use technology. So I will be sharing my screen with you to make sure that we can both see what's going on. So here we go. So this deals with the acid-base chemistry portion of AP Chemistry, which is probably the section that students have the hardest time grasping, but it's also the section that if a student is going to be pre-med or even just have to take chemistry again, it's a really, really important area. It's going to be on the MCAT, it's going to be in biochemistry, which is required for most medical schools, but it's also just a really important concept in chemistry overall. And so we're going to be looking at this one from 2021 dealing with methanoic acid. So we're going to read it together. Methanoic acid, HCOOH, ionizes according to the equation above. Write the expression for the equilibrium constant Ka for the reaction. So if you were my student, I would probably first draw your attention to the Ka. So Kas are only going to be associated with one very niched concept in chemistry. And I would hope that you know that it's weak acids. And then for weak bases, there's the Kb. And then I'd ask you probably what exactly is the Ka? Well, they told you it's the equilibrium constant. You might have also heard of it as the acid dissociation constant, which is the definition that the title that I prefer more than equilibrium constant, because it basically tells you how to answer this question. So write the expression for the equilibrium constant. So we're going to think of it as the dissociation constant. So if you've taken AP Chemistry, you might have already learned that weak acids only partially dissociate in water. And what does that mean? Well, that means that anytime in the solution at equilibrium, there's going to be some of this in the water and some of each of its parts that have dissociated. And it might be a little hard for you to sort of see that, but this ultimately, both of these come from this. And that essentially works through the mechanism of acid-base chemistry. The principle of acid-base chemistry is that this acid over here, methanoic acid, it donates this proton, and anytime a hydrogen is missing its electron, it's just a proton. And so it donates it, and it donates it all the way to water. And so that's how we get the H3O+. And then what's left over of this, well, it got rid of its proton, its positive charge. And so it's left over with this negatively charged, you might call it a salt. And that's what's left over. So when we think of that, the dissociation constant is going to be telling us what is the exact ratio of this, these pieces. So you might have seen it then as the pieces that it broke up into, so H3O+, and the salt or conjugate base left over the HCOOH. And so if we really think about this, it's telling us here's how much broke up and here's how much stayed as the weak acid and didn't break up. And so if this is really small, 10 to the minus 4 is really small, that means there's still a lot of this left over. That means you have a very big denominator compared to the top. And so you're already done with this question. As long as you understand what the dissociation constant really means, you're already done. Now the next one's a doozy. It's a lot harder. So it's asking us to calculate the pH of the 0.25 molar solution of methanoic acid. And so it's very easy for students to fall into the trap of hearing an acid and then seeing a concentration and immediately plug it into the pH equals negative log of either proton or negative log H3O+. And they just assume acid well, this is going to be the H3O plus concentration. That is not the case. As we already discussed, not all of it dissociates into the H3O plus. We have to figure that out. And there's a nice little trick for that, and it's called an ICE table. It stands for initial change equilibrium, and you're going to be dealing all with concentrations. So to start this, you're going to begin with rewriting the equation on top. Plus water goes to H3O plus and the conjugate base. So they gave us the initial concentration of our HCOOH. That's this, and they gave it to us, 0.25 molar. The thing about acid-base chemistry is you only have to deal with things that have aqueous associated with it. You don't care about anything that's liquid, and you don't care about anything that's solid. If you're dealing with pressure chemistry, you will have to deal with gases, but you're never going to see that in acid-base chemistry. You only need to deal with the aqueous. So how do you deal with that? If it's a liquid, you just say, I don't. You cross it out. You don't think about it again. Then we have our initial concentrations of H3O plus and our conjugate base. But you might not see any concentration associated with it, and that's because there is none. You're trying to make this. You're trying to make these. These are your products. So you're actually starting with nothing. So we'll just put 0 here. Now the next question is, how do I know how much changed? Like, how do we know here how do we know how much of this got used up? And we don't. So the nice thing about math and chemistry is that the way you signal that is you just put a variable there. And we know that we're using it up, so we're going to put a minus behind it. We're using this up, so minus X. And then the opposite is true for the products. We're making it plus X. So now equilibrium, you're just going to pretty much add up these columns, the I and the C. So we have 0.25 minus X, and we have X and X, because X plus 0 is still just X. So this might look like a whole bunch of nothing to you, but ultimately this tells us what we need to plug into this equation here. So we're dealing with our equilibrium concentration for H3O plus and the conjugate base, and then our equilibrium concentration of the HCOOH, or methanoic acid. So I'm going to write that up here. Ka is going to equal X for the H0 plus and X for the conjugate base over 0.25 minus X. Now you can solve for X, which will give you the concentration of your H3O plus, using the quadratic equation. But in this case, we can assume, because this is a really small number, so realistically, there's not much of this being made because it has to be over a very large denominator. We can assume that X is so small that it's negligible. So you can consider this X to be 0, that it's significantly less than 0.25, that it would really make that denominator, the change would be so negligible. So let's do that. So Ka equals X squared, I'm combining those terms on top, over 0.25. And this again, now just plug it into the original 1.8 times 10 to the minus 4. Now I'm going to solve for X. So ultimately I just multiply by 0.25 on both sides and then take the square root. The AP chemistry exam gives you a calculator, or you can bring a calculator and use it. So we have 1.8 times 0.25 times 4 minus 10 to the. I'm going to take the square root, and you get an equilibrium concentration, X, of 0.0067. But we're not done, because what did they ask us for? They asked for the pH, not the equilibrium concentration. we got the equilibrium concentration of H3O+, that's our X right here for the H3O+, but we have this nifty equation up here, which we wrote right at the beginning, where pH is going to equal our negative log of our H3O+ concentration, which is 0.0067. And if we do that, then we get a pH of 2.17. And pH is just in pH units. You don't need to put a unit with it. And so that's how you would solve this pH question. But if you can do something like this, and you have a good understanding of why I did every step, then you can solve almost any acid-base question. And so that's what I want to teach you guys to do. I want you to understand all of the concepts so that you can actually answer any question that looks like this one, or even doesn't look like this one, that is acid-base related. So I hope to see you guys soon. Bye.